We start this video by introducing structures. Structures are used to create more complicated data types than those already provided by C++. The simplest types are integers and doubles and strings. Now we will create something more complicated, and one structure that we will now create is a mountain. It's going to have three components. The first component will be called the name, the second will be the height, and the third component will be the location of the mountain. Since we are going to print something in this program, we will include IOstream. And structure mountain is created with this code. We declare the attribute. The first one is name of type string, the second one is of type double and its height, and the third one is location, which is also string. So, and now in the main function we declare the first mountain x by just typing this line. Now the object x will have three components, and we access and modify them by using the dot. So x.name, Mount Everest, is just going to populate this field name and place the string Mount Everest in that field. X.height is 8848.13 and x location is Earth. Something similar will now happen if we declare another object y, and we put the attribute's name is Olympus Mons, height is 21287.4, and location is Mars. We can create functions whose arguments are mountains, and one such function will be function that prints the data. We will just call it print data. Argument is mountain m, and the function will just return nothing and print a sentence that goes like this. On this function is now used by specifying its name and the argument. So now argument x will be passed and it will print Mount Everest on Earth has height 8848.13 meters. And the next call will have argument y, and the function will print Olympus Mons on Mars has height 21,287.4 meters. We will now compile this program and we will execute the program. Our new task is to create a function that modifies the argument. The argument will be a mountain, and the outcome of the function should be the mountain whose height is changed. This is the idea. Void change data mountain m, this is the input. All we want to do is change the height to 8448.13 844. And we will print changed to m dot height. After this function is created, we will first call that function before printing data of x. So we will change data to our mountain x. And now we will compile the program and see what happens. So the program prints changed to 8444, and Mount Everest on Earth has height 8848.13. So something unpleasant has occurred. It seems that inside the function the height was changed, and this message was printed in a way that we did not end up being surprised. We saw that the height was changed to 8444. However, when we asked the main function to print data, the height of x was not 8444, it was the old height. And this mystery requires a more serious analysis and drawing of memory diagrams to fully understand what was going on. We will now draw a memory diagram for this program. We start with a very serious command, mountain x. This is a very big request given to our computer. It says, please give me sufficient memory for one entire mountain and let me call that x. And this is what computer gives you. It gives you a big piece of memory because the mountain has 3 components. It has a name, it has a height. This is just one double, so it's a little bit smaller piece of memory. And it has location, which is another string. And since I will need all this space on my tablet, I'm going to decrease the size so there will be room for other stuff. So computer gives you this piece of memory and lets you call it x. Then this is the second command, which is essentially the same. You ask for a new piece of memory and you ask for permission to call it y. So that's what you will get. Then these commands, you're first asking for x.name to become Mount Everest, and that's what's going to be written in this location. Now we are running the command change data of x. This will call a function. The function is given by this code. So it's going to occupy its own spot in the memory. And so we will call it, we will give it a name here, change data. So The first command inside the function is mounting m. So what this really means is the function is asking the computer, please give me sufficient memory for one mountain and let me call it m. And the computer does that. So you get a new mountain and you're allowed to call it m. That's what our function can do. The fields name, height, and location are copied from the object x. So the name will be Mount Everest, the location will be the height will be 8848.13 and location will be Earth. So this is the consequence of the command mounting m. Now the command m.height equals 8444 is executed, and the consequence of that command is overwriting this data with the number 8444. The function will print changed to, and now it will read 8444. And the function now exits. So when the function exits, and that exiting happens when this bracket is executed, then this entire data is deleted from the memory of the computer. And we are left with our old friends x and y. We print data of x and we get unsurprising results that Mount Everest on Earth has the height 8848.13. And here is the summary of what just happened. The main function has a variable x. X is a mountain. The function change data takes one argument of type mountain and modifies its height. However, when we call the function change data and we supply the argument x, that argument gets copied. So when the function change data does its magic and changes the data, it actually changes the data on a copy, not on the original. And there was no desired outcome in our main program. The way how we will solve this problem is to use the addresses. The function main will send the address of mountain x to the change data. Change data will know the address and will not work on the copy, so it knows where the original object is located. It will go to that address and modify the real thing. So C++ tells us the address of an object in the following way. After printing the data, we will print the address. And this is the magical command that prints the address. I'm going to actually do something nicer. So if I just call this command, the address will be printed in a hexadecimal system. So to convert that to and have a beautiful number that we can read, I will use this conversion. Now we will compile and execute the code. the address was this very long number that I cannot pronounce. I will execute the code once again, and maybe once more. And so what we can notice is that in each of our executions, the address was slightly different. And there is a reason. That's not really surprising. When we execute the code, the object X is going to always be located in a different place in RAM memory. Today's computers have a lot of RAM, and whenever you are trying to allocate it to some of your objects, it's going to be in a different slot. Whenever you take a flight, you're always going to have a different seat. And whenever you book a hotel room, it's going to be a different number. And to prove now that our function change data is having a different address, I'm going to put one more line of code here. So now, once we have modified the code of the function change data, we will call the function. We will compile and execute this code. So inside the function, the address ended with numbers 28. Outside it was 00, 0. Clearly those two numbers are different. Now we have a plan. The function change data should have one argument that contains the address of X. We will call that argument AX. And the function should first go to that location. Go to AX. Once you are there, you will find a mountain. Once you find the mountain, access its attribute called height and change it to 8444. And inside main function, instead of change data of X, use change data of address of X. The type of the argument AX is not mountain anymore. The type is address of a mountain. And as you can expect, I did not tell you the whole truth. So in C++, the syntax is not go to AX, and it's not address of a mountain. So this new type of variable is called mountain star, and go to AX is, in C++ language, it is actually star AX. So our improved code will have here mounting star AX, and here instead of go to AX it will be star AX. These are quite different usages of the same symbol star. So star after data type means a new data type, that is address of. So int star means address of an integer. Double star means address of a real number. Mounting star means address of a mountain. Star before variable means go to. The data type is mountain star. The argument is AX, and we will go to star AX dot height equals 8444. Change data. The argument of the function is now not x, but the address of x. And then when we print the data, we will get everything we wanted. It's going to be the best print of the day. And we are getting to the last topic for this video, and that's linked lists. We want to store large quantities of data in our computer. We learned how to store two mountains. We gave them the names X and Y. But if we have a lot of mountains, way more than the letters of alphabet that we know how to pronounce, then we want advanced data structures. So we will for this video assume that we want to store 3 mountains and that we are stuck after X and Y. We have no idea what comes next. So we want to figure out something smart. And the way to do that is that each element of the list will keep track of the next. So the first mountain, in addition to its name, height, and location, will have one more component, and that will be the address of the next. And the next mountain will have its name, location, height, and the address of the next mountain. And it will go for many mountains. Each node of linked list has 2 major components. The first component is called content, and the second component is address of the next term. The content in itself is a very complicated and big object. It's a mountain, and it will have its 3 components: name, height and location. So we are going to have 3 mountains. Each of these objects will have its address in RAM memory. Our first mountain, Mount Everest, will keep track of the location of our next one. So this number 140 that I cannot really pronounce should be stored in this location A next. The next mountain, Olympus Mons, will store the location of our third mountain, Mauna Kea. And Mauna Kea is the last mountain in our story, so it will store some special symbol saying I am the last. In C++, the convention for this special symbol is null PTR, that stands for null pointer. Our graphical representation and memory diagrams would be extremely difficult to draw if we have to invent these crazy numbers every time. Instead of making up the numbers and putting them as addresses of our variables, we will just keep the arrows. And so instead of these two numbers, I will just keep an arrow that starts from A next and points to the new mountain. So this arrow means that whatever the address of the object that has Olympus Mons is, that address is stored in the A next component of this object, Mount Everest. List node. The first component is of type mountain, and we will call it C. It stands for content, and address of the next list node, and it has to be of the type list node star. And it's time to type out our first program with linked lists. We will use our old source file in which we created the mountains X and Y. We will now declare the structure list node with two components. First component of type mountain, and that component will be called C. It stands for content. The second component is the pointer or the address of the next list node. Now I will declare 3 list nodes: first, second, and third. The first one will have content equal to X. The second one will have content equal to Y. And the third one is going to be Mauna Kea. As we discussed before, I don't really need a variable for Mauna Kea. I can access it through third.c.name is Mauna Kea. Third.c dot height is 4207.3, and third C location is Earth. And now I want to wire these pointers correctly. First dot A next is address of the second. Second dot A next is the address of the third. Third dot A next is a null pointer. Now I will create the function that prints the entire list. And the most elegant is a recursive function that will receive the address of the first term. And why is this going to be elegant? Because it will print the content and then it will recursively call the same function but with the argument A next. So I'm now going to print the function here. Void print list. And list node star A first. Its argument is the address of the first term. I have to ask the question whether this is a null pointer. If it's null pointer, I should do nothing. But if it's not null pointer, then I first print the data. Print data is a function that expects mountain to be its argument. So I will go to the address A first. At that address, I will find a list node. List node will have two components, and the component called C is a mountain. That mountain is the perfect input for the function print data. After I printed the data of my mountain, I now call the function print list and I pass the argument star A first dot A next, address of the next. And now I have my perfect printing. We will now save the file, compile, and execute the binary. We will solve the following problem. The user input consists of positive real numbers that end in a negative number. At least one of the numbers is positive. Create a linked list from the numbers given by the user. And this is the example. If the user gives us the numbers 9.7, 1.7, 2.7, 3.7, 7.7, and -3, we should create the list that has the first component 9.7 and the second component is the pointer to the second term. I could give the names to these list nodes. I could call them first, second, third, fourth, and fifth. But as the numbers grows larger and larger, I would be running out of my vocabulary to give the names to the list nodes. So what I will do is I will declare just a pointer list node star address of the node, and I will use the command new. The command an is new list node. And now I will explain to you what these two commands are. The first command is, dear computer, please give me sufficient memory to store one address. So I'm now asking for a very modest amount of memory. I only want to store an address of a list node. And computer gives me a piece of memory capable of storing an address of a list node, and computer lets me call it an. The line an is equal new list node has two commands actually. The first command is new list node. This means, dear computer, please give me a memory capable of storing the entire list node. And so the computer gives me a lot of memory. And the second part is this sign. So this sign is that memory will have an address. And that address is some number that looks like this. Please store that number in an. And so graphically we represent that in a nicer way. I will take an arrow that starts at an and ends in the top left corner of my list node. Since our program will do some printing, I will include iOS 3. We will need our structure list node, and in my main function I will need one variable of type double that I will call uInput. It stands for user input. I will now read the user input from the cin, and as I read the first user input and take for granted that this first input value will not be negative, I am ready for the first list node. I will call it an, that stands for address of the node. An is new list node. And I will assume that the user will first give me 9.7. That's the first user input. The command an equals new list node results in me receiving sufficient memory for one list node that has two components, C and A next, and the address of this list node is stored in the variable an. Star an now means go to the address an. Once you go to the address, you will find the list node. Once we follow this address star an, we will go and find one list node, and now I will access its component C and place the number U input inside. So this will now receive the number 9.7. I will at the moment also access the second component A next and put null pointer there. Because at this very moment I don't have other terms of the list. I have to wait for user to give me the other terms. My variable an will be used to create all of the other list nodes. While doing so, I may run the risk of losing the address of the very first list node. And that very first list node is very special, because if I know the address of the first, I can keep track of the entire list. So to save the address of the first list node, I will declare one more variable, list node star AF, and that stands for address of the first. AF will be set to be the same as AN. So AF is address of a list node, and at the moment it's the same as AN, which means it points to this node. Now we read the next value from the user, we store it in the user input, and we agreed when we run this program we are going to put 1.7 as the next value. Now we will have a while loop. While user input is positive, once we verify that the user input is positive, we have to create a new list node and properly identify a location where the address of this new list node will be stored. But let's focus first on this command. New list node means, dear computer, please give me sufficient memory for one list node and store its address at a very special place. That special place is here. And that special place can be accessed through AN. So AN knows the address of this list node, so we will access this special place by typing star AN dot A next. Now my address AN, address of the nodes that I'm creating, is going to be changed. I don't want it to point anymore to the first term. It should now point here. So I will achieve that by writing AN equals star AN dot A next. and then I will put my number 1.7 here using the command star an, because now my an points here, so star an dot c is user input, and star an dot a next is a null pointer. So now I have here null pointer. I read the new value from the user and go back to the beginning of the loop and keep repeating the procedure. In the new run of the while loop, I'm going to keep the promise and insert 2.7. When that happens, the command new list node will result in the very new list node being created, and its address will be stored in an star dot a next. So I will follow an, I will find this list node, and then this a next slot will have the address of the newest element of the list. The command an equals star an dot a next means that this an will be erased and an will point here. This command will now change the content and it will become 2.7, and the last command will put null pointer inside this field. And the terms 3.7 and 7.7 are the last two terms in the list, will be treated in the very same way. So in the end, I will have two functions, print list, and I will pass af as an argument, and this function will print the list. And we will use delete the list that will make sure that we deallocate the memory. Without delete, we are running a risk of having a memory leak in the case that we are making bigger programs and that we are using several lists and some temporary lists that have to be returned to the computer. So this is the end of the main. It remains to create the source file, type the code, create the binary using the C++ compiler, and execute the code. We have already created the main function, we have created the structure list node. It remains to make these functions print list and delete list. We will first create print list. Its argument will be of the type list node star, and this is going to contain address of the first element, a first. First we check whether the a first is different from null pointer, and if it is different than null pointer, we print the content and the space character after it. And then we call the function print list with the argument star a first dot a next. And if we comment out the function delete list, this will compile, and when we execute it, it's going to look like everything is okay, except that the program has a memory leak that at the moment will not cause problems because the function main exits at this point and there will be no other commands, so the operating system will automatically clean the memory. And maybe after I print the list I should print end line. And then everything looks so nice. So it remains to deallocate the memory. The function delete will tell the operating system, I don't need the memory that is at this address. So delete list will be a recursive function whose argument will be the address of the first term, and we check again if a first is not null pointer, then we first delete the list of a first dot a next. After that term is deleted, we use the command delete a first. And I can actually even type something. Deleting the node whose content is a first dot c. Now when I call delete, so we see that the terms are deleted in the opposite order of the list, or the term that was created the last was deleted the first. This is the end of the video. The codes and more examples can be found on the course website. Thank you for watching this video and congratulations for seeing its end.